It all began with the battery light on my dashboard, which one day decided to stay on after starting the engine. Finally, I decided to make a video where you will see how to test each element of an alternator with a simple multimeter. Like for example, the regulator, the windings of the rotor, the diodes of the diode bridge, and so on. I will try to be as clear as possible by showing each time the diagrams of what I test. The idea is to understand how each element works and to replace only the one that doesn't work. If obvious first, it is the alternator which doesn't work, and that is what I'm going to look in first time. Hello everyone, so here is my battery indicator light stays on while the engine is running. But why? First I accelerate a little. On some old cars, it's just that the engine runs a little too slowly. Here the light remains on anyway, so it can't be a battery issue since the car starts perfectly and everything works fine. Now the first question to ask is, does the alternator turn? And here yes, it turns. So it's not the belt that's broken. On some alternators there is a disengageable pulley. If this is broken, the pulley turns but the rotor inside the alternator no longer turns and therefore the alternator no longer works. This cannot be my case today, because this alternator has a conventional pulley which is therefore not disengageable. Now I am looking to see if the battery is charging. Effectively, it could be just a light issue. To be sure of that, I measure the battery voltage with a voltmeter. On this BMW 5 Series E39, there is a positive terminal here, and the negative pole. I take it anywhere on the car body. I start the engine, and I have the answer. I should have at least 13.8 volts while there. I read 12 volts only. This means that the battery is not charging. If you have 13.8 volts or more, it means that your battery is charging, but you have a problem with the battery light. The light is on when it shouldn't. In this case, you can drive, but you will still have to solve this indicator light problem. I advise you to look at the fuses first, but in my case the battery does not charge. I can drive, but as long as the battery has enough energy to power the systems. The engine needs electricity to operate, to power the engine control unit, the fuel pump, the fuel injectors, and so on. I was able to drive about 2 hours, and then, it has been the breakdown. Now I want to know if this is really an alternator issue, or if it is another issue on the car. Effectively, I could have a blown fuse, a disconnected or cut cable for example, which would mean that the alternator has no issue. For that, I show you the connection diagram of the alternator. The alternator is here. It is connected to the car by 3 points. It is connected at the negative pole of the battery through the car body. There is no connector. It is the metal body of the alternator which corresponds to the negative pole. Then it is connected to the positive pole of the battery by the big red cable. But it is also connected to another pin named ignition. In summary, it's as a positive signal after the car is turned on. Before incriminating the alternator itself, I will first test the 2 positive connections. And for that I have to remove some parts around it. When you work with electricity, I advise you to disconnect the battery. And of course I would reconnect it back in to do the tests. On this car, I have to remove the intake airbox to easily access the alternator connections. Now I can see more clearly. I didn't show you, but to do this test, I have reconnected the battery. I will first look that the big positive connection is well connected to the positive terminal of the battery. On the alternator, it is under a big rubber. I measure the battery voltage well, so the big connection B+ is well connected to the battery. Then there is another cable connected to the alternator. I unplug it. And what interests me is the middle pin. This pin should change to a positive voltage once I turn on the car. I have just added a little wire in the middle of the connector. And I look at the voltmeter that the voltage increases well once the car is turned on. So there I read 0 volt and the car is turned off. I turn the car on. And I read almost 9 volts, so that's good. It means that the alternator has received the enable command from the car. I don't measure exactly the battery voltage, but that's because the ignition signal is controlled by the engine control unit, which can decide to disable the alternator in certain situations. Well, now I'm sure the issue comes from the alternator and not from the connections in the car. Now I remove the alternator and test it on the table. Here is the alternator removed. Now I will test it with a drill. I connect it to a 12-volt battery. Here it's a motorcycle battery, but the voltage is exactly the same as a car battery. About connections, the negative terminal of the battery goes to the alternator body, and the positive terminal of the battery goes to the B+ pin, as well as to the middle pin of the small connector. And I added a voltmeter to measure the battery voltage. To make it turn, I use a corded drill, simply because cordless drills don't turn fast enough. Let's go. Well, unsurprisingly, the battery voltage does not increase. I should read at least 13.8 volts. That means that the alternator is not working at all. Before opening the alternator, I will just do a little parenthesis on its operation. And yes, you notice that it takes a battery to test it. This is because the alternator is not a dynamo. It may seem paradoxical, but the alternator needs energy to then provide more. Let me explain. Here I symbolize the stator of the alternator, or the not turning part, with a small winding taken from an old relay. In order to display the maximum voltage measured, I connect it to a voltmeter that I put in AC and max mode. I start by taking a magnet which symbolizes the rotor, and I move this magnet in front of the stator. There is a small voltage, and if I go faster, well, the voltage increases. So what I just did here is a dynamo and not an alternator. In fact, in an alternator, there is no magnet at all. The rotor is also a winding. I take this, and what happens if I move that rotor there in front of the stator? Well, nothing happens at all. The rotor is not magnetized, and therefore the stator does not generate any voltage, so I measure 0 volt. The way for the rotor to behave like a magnet, I have to supply it, and I do it by connect it to the battery. And now it works. I measure a voltage. And what happens if I supply the rotor with a lower voltage battery than this battery? Well, it still works, but I measure a lower voltage. In fact, since the alternator cannot choose its speed of rotation, it will vary the voltage in the rotor in order to have the correct voltage at the output of the stator. Now I can show you the diagram with the internal parts of the alternator. I will introduce the parts and their role, and then I will show you how to test them independently. First, here is the regulator. It is supplied by the battery and it supplies the rotor here. When the ignition pin has a positive voltage, it adjusts the rotor voltage in order to have about 14 volts at the battery. When the ignition pin is not supplied, the regulator does not supply the rotor at all, and the alternator does not work, and that is a normal behavior. It is just disabled. Moreover, when the rotor turns, it is powered by brushes shown here. Now here is the stator. The stator is the fixed part of the windings, and there are several windings. Here there are 3 windings connected in star at a midpoint M, so no, it's not the time convector.
This is what makes time travel possible.
Finally, the voltages that come out of the windings are alternating, so these voltages must be rectified in order to have a positive voltage to charge the battery. And that is the role of the diode bridge, which is here. The diode bridge is made with 6 rectifier diodes. Now I open the alternator, and I'm going to show you each part. I have just 3 nuts to remove. Done. Now the stator is behind the fixed part here. And you can see the end of the rotor here, which is supplied by copper slip rings. The diode bridge is the big black part here. And finally, the regulator is here. The easiest way is to remove it. There are just 2 screws to remove. I can see that the brushes are not damaged and have the same length. So it's good. It's important that these connections are good. The connections are clean. A very simple first thing to do is to check that the rotor winding is not cut, that it is not in short circuit, and that it is well connected to the slip rings. To do that, I put my multimeter in ohm meter mode, and I measure the resistance between the two slip rings. I can't read the value immediately, and it's normal because the windings have a strong inductive effect. I measure about 3 ohms. It's good, it is a correct value. Now I'm sure that the rotor winding is well connected to the slip rings and that it's not cut. Another very straightforward test to do is to check that the rotor winding isn't in short circuit with the metal body of the rotor. I put my multimeter in continuity tester. It is the same behavior as the ohm meter, except that it beeps when the measured resistance is very low. When I touch one of the slip rings and the metal shaft of the rotor, it should not beep. It doesn't beep. Good. Now I know that the rotor has no issue. For those who are wondering if it's possible to read the value of the inductance, the answer is yes, and I'll show you that later in the video. Now I will show you how to test the regulator. I remind you, it is this part which supplies the rotor through the brushes. For that, I take the battery and the multimeter in DC voltage mode. The metal body of the regulator corresponds to the negative connection. I connect it to the negative terminal of the battery. And I connect the positive terminal of the battery here, on this pin through the spring contacts. I follow the connection and I connect the wire here. Now nothing should happen. The regulator is disabled because its ignition pin is not enabled. I measure the voltage on the brushes. And I measure almost nothing. The scale here is in millivolts. Now I enable the regulator by connecting the ignition pin to the positive voltage of the battery. The voltage measured on the brushes is 4.5 volts. This value is not correct, it's not enough. The voltage should be almost the battery voltage, which is around 12 volts, so this regulator is damaged. And I have a good news, I have a new one. Here. Now I show you the same tests with the new regulator. First I reconnect it to the battery without connecting the ignition pin. And there I measure a few millivolts between the brushes. It's good. It means that the regulator is disabled. I enable it by connecting the ignition pin to the 12 volts of the battery, and there I check the voltage on the brushes. And I measure more than 11 volts, which is almost the battery voltage. It's a correct value. It means that this regulator can supply the rotor well. Now I want to know if the alternator works well with this new regulator. I refit the new regulator. And I connect the alternator as before. And go. Well, that doesn't work. Remember, I should measure at least 13.8 volts. That means that there is another issue elsewhere in the alternator. So now I will check the stator and the diode bridge. For that, I remove the new regulator. And I remind you, the diode bridge is the big black part here. In the diode bridge there are somehow 3 areas. The top area is the plate here. It is connected to the positive voltage. Then the area below or this plate here corresponds to the negative voltage. And in the middle area, here, there are the connections between the diodes and the windings of the stator whose ends are soldered here. There are 6 connections because the midpoint M is also connected on this plate. The diodes are here. Those are the little circles you can see here. On this diode bridge, there are 6 diodes in all. There are 3 diodes on the positive side, and you can see the tail of the 3 diodes on the negative side. So the first test I can do is very simple. If you look closely at the diagram, the ends of the windings should not be connected at the positive side or at the negative side. I take my multimeter in continuity tester mode, and I will check that there is no short circuit between the ends of the windings and the negative side or the positive side. I put one probe on the body of the alternator, which is the negative pole, and the other probe on the end of the windings. And beep. That's not good. It shouldn't beep. It beeps on all 6 connections, so it means that there is a short circuit somewhere. I didn't show you, but it doesn't beep when I do the same test on the positive side. There is a short circuit on the negative side only, and to find the short circuit I have to remove the diode bridge in order to separate it from the windings. To remove the diode bridge, I begin by removing the 3 screws. Then, I see the ends of the windings which get into these plastic guides here. These connections are pinched and soldered. So I tried to remove the solder with a soldering iron and a heat gun like that, but I didn't succeed. So I cut the plastic guides and pried off the ends of the windings with a cutting pliers and a flat pliers. So be careful, I don't cut the wires of the windings, I show you. Here you can see, the end of the windings is released. I do the same operation for the other ends. Now it's okay, all the ends are released. I can finally remove the diode bridge. Since I've separated the stator windings and the diode bridge, I'll start by testing the stator windings first. You can notice that there are 2 wires at each end. This is normal. It's simply because the windings are assembled in pairs. In fact, there are not 3 windings, but 3 pairs. I didn't want to complicate the diagram either, and that doesn't change the tests I'm going to do. First, I take the continuity tester and I check that the windings aren't in short circuit with the body of the alternator. 1 okay, it doesn't beep. 2 okay. 3, 4, 5, both wires okay. And 6, perfect, there is no short circuit. Then I check that the windings aren't cut, so the tester should beep when I touch both ends of the same winding. It's okay. Moreover, the windings shouldn't be in short circuit with each other. So the tester shouldn't beep between 2 different windings. Here it is good. I check the next one. Okay, it's not cut. And this winding isn't in short circuit with the last one. And the last one. Beep. It's good. In summary, I have 3 pairs of windings which work well and which are not in short circuit neither between them nor with the body of the alternator. I can deduce that the stator is good and that the short circuit should be in the diode bridge. Before checking the diode bridge, I do a second parenthesis. I just want to show you another measurement you can do on the windings. I do it with this device. It looks like a multimeter, but it's not really a multimeter. It is an LCR meter. With this device, I can measure resistances since there is an ohm meter, but I can measure inductors and capacitors too. I'll start by measuring the inductance of the rotor winding. On the rotor, I measure 20 millihenries. And on the stator, I measure 82 microhenries on the first stator winding, 79 microhenries on the second one, and 84 microhenries on the last one. I show you these values just to give you an idea of those magnitude. It's just important to measure roughly balanced inductance values, so it's okay for me, and I confirm that the stator is in good condition. Now I close this parenthesis and I'll check the diode bridge. Here is the diode bridge. The midpoint M of the windings is on the 3 pins connected here. Then here it's the positive plate side. The positive pole of the battery is here. The positive pole is connected to the regulator by this contact. The positive diode of the first winding is connected like this. Then the positive diode of the second winding is connected like this. And then the positive diode of the third winding is connected like this. And now I flip the diode bridge to show you the negative plate side. The negative pole of the battery is connected to the body of the alternator by the 3 screws. The negative diode of the first winding is connected like this. Then the negative diode of the second winding is connected like this. And finally, the negative diode of the third winding is connected like this. I begin by checking the simplest thing. I check that the 3 pins of the midpoint M are well connected to each other. Beep, it is connected. Here it's also connected. And of course, it's connected here too, so the connections of the midpoint M are good. Now I check the diodes. I put my multimeter in diode tester mode. You can test a diode like that. You have to connect the probe of the multimeter's positive terminal to the anode of the diode and to connect the multimeter's COM terminal to the cathode of the diode. If the diode is in good condition, the multimeter should display about 0.6 volts. This voltage corresponds to the threshold voltage of the diode. I begin by testing the 3 diodes on the positive side. I am testing the positive diode of the third winding. I measure about 0.6 volts. That means the diode is good. I do the same thing with the positive diode of the second winding. 0.57 volts, it's good. And the last positive diode of the first winding. These diode is good too, so all the diodes on the positive side are good. Now I check the negative side of the diode bridge. I connect the positive terminal of the diode tester to the negative plate. This is where the anodes of all the diodes are connected, and I am testing the negative diode of the third winding. Oh, I measure 0, that's not good. If the measure is 0, it means that the diode is in short circuit. Well, I have therefore found the issue on this alternator. I still check the last 2 diodes. The negative diode of the second winding is good, and the negative diode of the first winding is good too. In conclusion, this diode is damaged. This diode is in short circuit, and that is the reason why the alternator does not work at all. I remind you, in a diode that works correctly, the current can only flow in one direction. It flows from the anode to the cathode. You can imagine that a diode is an arrow that gives the direction of the current. In the other direction, it is a barrier, and the current cannot flow. If all the diodes are in good condition, the current generated by the windings can flow like this. It gets out of the windings, flows through the positive diode, flows into the battery and allows it to charge, and then the current returns in the alternator through the body, then flows through the negative diode to end up in the winding. The loop is complete. Whereas if one of the diodes is damaged and behaves as a short circuit, the current flows directly into it. It creates a current loop inside the alternator, and it obviously does not charge the battery. So maybe I could just replace the diode in the diode bridge, but that's not that I'm going to do. I'll refit a new diode bridge. Before that, I just show you the same test done on the new diode bridge. And here I read 0.63 volts on the diode tester, so this diode bridge is good. Now I'm going to refit the new diode bridge on the alternator. I start by removing the excess solder from the ends of the windings. In order to not dirt the alternator with solder, I protect it with a paper towel. Then I clean the solder with a soldering gun and a wet sponge. I don't show you everything, I've done the other ends. You can also use a desoldering pump to remove solder. Once it's finished, I remove the towel and I shake the alternator to remove any dirt. Nothing should be left in it. Now I am going to lengthen the connections a little bit because otherwise it will be difficult to solder them to the new diode bridge. To ensure reliability, I hold the new wire by wrapping another small wire around it. Then I solder the hole. It must also be not too thick, otherwise it will not pass through the plastic guides of the diode bridge. I show you that on one wire. Here I've already done 2 wires. I take a very fine thread cotton multi-wire cable. I start to wrap it around the wire of the windings. Then I place a big wire. It's a big electric cable, and I wind the tiny wire around. It holds, but I add a little more wire. Then to solder that, there are 2 methods, knowing that the one with the electronic soldering iron like this one does not work at all. The first method is with a heat gun, and I will show you the second method when I'll solder the diode bridge. I put the heat gun at the maximum temperature, and I direct the hot air upwards so as not to burn anything. I first warm the connection up, and then I bring solder. I put it on top so it will flow. Here, I wait for it to cool down and I cut. Now I finish all the connections. It's done. And I refit the new diode bridge on the alternator. I screw it back. And then I'm going to hold the wires together by pinching them. And then I solder them, and this time I take a soldering gun. Here I have already made a solder, and I show you the second one. I put some solder flux on the solder connection first. The solder flux is a kind of paste which allows the solder to flow well. I take the soldering gun, I set it at the maximum temperature, and I use the larger tip. I heat the two parts, then I bring the solder. The solder should flow onto the wire and the diode bridge connection. Done. And then I cut off what is extra. Now I finish the other 4 solders. I have finished. Now I refit the regulator on the alternator. And I test the alternator in the same way as before. 14.4 volts is good, the battery is charging, it works well. I finish by refitting the cover, and I refit the alternator in the car. Are you ready? I start the engine. And the battery indicator goes out. It's good, the issue is fixed. And how much is the charging voltage? Well, the charging voltage exceeds 13.8 volts, that's okay. This video is now complete. I hope you liked it and was useful to you. The thing one can still wonder is why there were 2 damaged parts on my alternator. So my hypothesis is that it heated up because of the damaged diode, and that it then damaged the regulator. You can tell me what you think in the comments below the video. You can also share it, put a thumbs up, or consider subscribing to the channel. And see you soon on Enjoy Wheels.